back. This happens to be our Chapter 11 free response AP problem, yay, our FRAPPY, right? And our setup here is that as a project, some AP Stat students were tasked with determining if including additional information in a survey question would change the distribution of responses. Right? So we're looking at, hey, are we changing distribution? Okay, so that's important to know. Okay, so then we look further, and it says, to find out, they randomly selected 30 teenagers and asked them one of the following questions. 15 were randomly assigned question A, the other 15 were assigned to answer question B. And we have the questions. Okay. The table summarizes the data. The chi-square test statistic is 6.12. Right? You can always check to see if you want to find that chi-square test statistic, right? Remember that it is the summation of your observed minus your expected value. So the difference between observed and expected squared all over expected, right? And if you were to do that for each of our pieces, you'd be able to get there. Okay. Now, how we find these expected values will come up a little bit later. But for now, what would be the hypotheses that the students are interested in testing? All right. Pause the video, think it through, provide your answer, come back and check. So, the null hypothesis would be that there is no difference in the distribution of responses, right? Because we're looking, was there a change in the distribution? So we'll say, hey, there is no difference. There was no change. And the alternative is that there is a difference in the distribution of responses. Now, this would be if we were to do a test, a chi-square test for homogeneity. Right? How do we know it would be a chi-square test for homogeneity? Well, we controlled whether they received question A or received question B, and we then can consider that as our two samples rather than just one sample. And because of that, and we're looking at this categorical data, that would be a chi-squared for homogeneity. Okay? Now, that's if we could do it. But if we look at part B, why is it not appropriate to use a chi-square distribution to calculate the p-value for this data? Well, think about that. Come back, check it out. So first we start with our random condition. Well, we had random treatments assigned. What was the treatment? Did they get question A or question B? Right? And the treatment was this additional information. It's sad that some people choose a college based on its athletic program. Okay, so we did have a random treatment assigned because they were randomly assigned to those questions, and therefore our random condition is met, and our 10% is not needed because it's an experiment. Our independence is there from our random assignment and treatments. So what's the only thing that's left? The only thing that's left is our expected counts. Right? Well, what do we know about our expected counts? Our expected counts all need to be greater than 5. Okay? So if it's telling us it would not be appropriate, that's basically telling us that not all the expected counts are going to be greater than 5. How do we find those expected counts? Well, a way to find the expected counts is to look at my matrix and look at my marginal distribution on my matrix. Right? This notation we can say is going to be our expected count for row 5, column 2. Right? So it's going to be my expected count for that position. Right? 1, 2, 3, 4, 5, row 5, second column. How do I find that expected count? One way that I can do it is to say, hey, I'm going to have my row total times my column total all over my total. But really what's happening? Really we're saying, hey, if there was no difference in the distribution, right, how many answered not important at all? 6 out of 30. Right? So 6 out of 30 answered not important at all. Now, If that's the case, how many would we expect to be from question B? Well, there was 15 total that answered question B, and the percentage of them responding not important at all was 6 out of 30, so that would be 6 out of 30 times 15, which is equal to 3. But of course, the shorthand is to say row total, column total, divided by total. And that's 3. So our expected counts are not all above 5. So that's why it would not be appropriate. So what do we do then instead? Well, to estimate that p-value, 100 trials of a simulation were conducted, assuming the additional information did not have an effect on the response of the question. All right, that's our null. Assuming the null. In each trial of the simulation, the value of the chi-square statistic was calculated, right? So they went through simulation, right, and calculated the chi-square. Okay. These simulated chi-square statistics are displayed in the dot plot, right? We can kind of see, right, that general chi-squared right skewness shape that we have there. And based on the results of the simulation, what would we conclude? Well, our chi-squared value was 6.12. Based on the simulation, right, if 6 is down here, right, all of these data points over here, all of these, right, all of those are more than the 6.12, right? So that tells us that what? It tells us that we have many simulations with chi-squared at least 6.12. I don't feel like counting those up, but it's certainly more than 5 out of 100. Okay, so we have many simulations with the chi-squared at least 6.12, so we're going to fail to reject the null hypothesis. Right? So what's going to be our conclusion? We do not have convincing evidence that the distributions differ. Right? Now, does that mean that distributions do not differ? No. But we don't have convincing evidence that they do differ. That's very important. If we were to have made a mistake, this would be a type 2 error because of failure to reject. The probability of that would be beta, right? All of that information we still need to recall. Right? But in this situation, chi-squared 6.12, possibly we got our results due to chance. Okay. Always ask questions for clarification. Hopefully the FRAPPY made sense. Be sure you're preparing well. Good luck on your assessments that are coming up.